Welcome to the SecurityTube Linux Assembly Expert 64-bit edition. Now in this video, we will look at moving data using assembly language. Now, if you've looked at the 32-bit assembly language video tutorials, then please be warned that there is something super important you need to keep in mind. And that is that in 64-bit mode, the operand size, and I'm pretty much quoting this verbatim from the Intel manual, simply because it is that important. So the operand size determines the number of valid bits in the destination general purpose register, right? The first one is self-explanatory. 64-bit operands generate a 64-bit result in the destination GP register, right? The second one is what is really super important. 32-bit operands generate a 32-bit result, 0 extended to a 64-bit result in the destination GPR, right? And if you're confused about what this is, I'll just explain this to you in a minute, with an example. Finally, when we do 8 and 16-bit operand operations, then the upper 56 or 48 bits, right, are not modified. Now let's jump in and I'll clarify what I mean in the next couple of minutes. Now, the most common instruction in assembly language is the move instruction and its variations. Allowed direction is between registers, between memory and register, and vice versa. Immediate data to register and immediate data to memory. We've seen a couple of examples when we did the Hello World program and others. Now, LEA or load effective address allows us to load pointer values into registers. So LEA, RAX, and then the label within square brackets would actually give us the address which label references. Exchange goes ahead and exchanges or swaps values between register and memory, right? Now these three are probably the more commonly used data movement instructions. There are others which you can also refer in the Intel manual. These are also the common ones used when we will look at other advanced examples like in shell coding. So let me jump right into the lab and basically illustrate how to use these different instructions as well as what we discussed on the very first slide. So I have my 64-bit Ubuntu running here, and what I've done is I've just logged into it over SSH just so that I can get a little bit more screen real estate. And you can download a program called movingdata.64.nasm from below the video, right? You should see a link, and this is how this looks like. It's a simple program to illustrate the different data movement instructions which we have spoken about. Okay. Now, moving an immediate data to a register, right? So I'm moving all of these immediate data values into registers. Here is an example of moving 64 bits of data, into RAX. Here is an example of moving 32-bit data into EAX. Here is an example of actually moving 1 byte into AL, again 1 byte into AH, and a couple of other examples, right? Then we have moving values between registers, and then after that moving from memory into register. Now you see sample, sample2, etc. All of these have actually been defined in here. At the bottom. after that, we have moving values basically from the register into memory. And I've taken different examples in here. Then we have the LEA demo, and then finally the exchange demo, right? And then we exit the program gracefully at the very end. You can use Pico and Nano as well. Let's assemble and link the program. Of course, if you run the program, pretty much nothing happens. It just exits, right? Now, let's actually use GDB in TUI mode to step through the program and understand these instructions. Let's break and start, run the program, layout ASM, layout registers, and we have all of them, right? And right now, basically, RIP is pointing to the very first instruction which we are about to execute. And we talked about move and move ABS in a previous video. So which is going to move the immediate value, you know, A, B, 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 B into RAX. So let me use step I, and just notice the value of RAX is 0 at this point. And if you notice, after the instruction executed, the long immediate value has been put inside the RAX register. Now, here comes in the important part, right? If we go back to the slides, the first part is absolutely okay, 64-bit blah blah blah. The second part, 32-bit operands generate a 32-bit result, 0 extended to a 64-bit result in the GPR. Now the next instruction actually moves basically 4 bytes of all A's into the EAX register. Now what this will end up doing is it would go ahead and occupy the lower 4 bytes of RAX while going ahead and 0 extending the upper 4 bytes. And this is something very, very important to remember, right? So let me do a step I once again. And if you notice, basically right now EAX contains all A's while the upper 4 bytes of RAX were zeroed out, right? This is very, very important. Keep this in mind. And I think, you know, if you have this in mind, pretty much there isn't anything else you need to worry about from a move instruction perspective. Okay, let's once again move the same old value inside RAX. Now, when we are dealing with 8 or 16-bit operands, we needn't worry because the upper 56 or 48 bits of the GPR is not modified by the operation. Fair enough, which means when we transfer 11 into AL, right, which means the last byte would actually be 11, the rest of the bytes would remain untouched in RAX. Let's verify that. And here we go, right? Just the last byte changed to 11. All the upper bytes were not touched. Now in the next instruction, let's again set RAX to that default value. And similarly, when we change AH to CC, none of the other values are tampered, as you can clearly see on top here. Similarly, when we go ahead and play with AX, right, nothing else changes apart from AX. Now, let's look at moving data between registers. So now I'm copying RAX into RBP. At this point, RBP is 0, but after this instruction, as you can clearly see, it contains the same value as RAX. Similarly, there are a bunch of others which you can play around with and have a look at. Now coming to this instruction, move RSI, and we see a keyword pointer, blah blah blah. Now this is interesting from the perspective that we had defined those three variables, right, which we can find by typing in info variables. So sample, sample2, and sample3. Now here is what we are doing. Sample2 is really at this address, which is 060017C, and we can see that in here. Now what does that contain? So let's examine it, and we need to interpret that as a keyword. So I think x/g ampersand sample2, right? Let's actually go ahead and print this in hex, x/xg ampersand sample2. And we can see the value 1122334455667788. And after this instruction, this is what will be inside RSI. So let's go ahead and locate RSI. Here is our friend RSI. Let me do step I. And there we go. RSI now contains this value, which was fetched from that memory location. Fantastic, right? Now the rest of the instructions of moving to and from memory to register, play with it yourself. Simple enough. Now in this instruction, move byte pointer, ds colon blah 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 comma al, we are going to do the reverse. Now what is there in the AL register? The value 88. And now let's see what is there in this specific memory location, right? 174. Now if you again just do an info variables, you'll see that 174 is nothing but sample, right? So let me print this x/4xb. Let's print it as bytes because AL is just going to transfer 1 byte, ampersand sample. Okay, and AL contains the value 88. So let's run this instruction. Let's go back and look at the value of sample. And if you notice, the value AA was overwritten by 88 in memory because of this specific move instruction. Fantastic. Similarly, you can try out the rest as well as far as moving from register to memory is concerned. Now we come to load effective address. Again, load effective address really is concerned with loading the address where this specific value is actually going to be located. So it's super simple. Let me execute the command. And what you would actually end up seeing is that this ended up going ahead and copying the pointer value inside RAX. Now similarly, you can go ahead and hit another enter to copy that into RBX, which again the same thing ends up happening. And after that, we actually go ahead and load an immediate large value into RAX again, same with RBX, and then we use the exchange command to exchange RBX and RAX. So here is RAX, here is RBX, exchange is going to swap them. And there we go, right? They've been swapped. Fantastic. And then finally, we have the exit sys call to exit from the program. And there we go, right? So now you've noticed using the TUI mode, how simple it can get to quickly trace through a program and see what is happening. So hopefully you've enjoyed this video. And that's all I have In this one, try out the example by yourself by downloading the code, and hope you're enjoying your time in Pentester Academy. And if you like what you see, we'd really appreciate and be thankful if you can recommend us to your friends and colleagues in the InfoSec community. That's all. Thank you very much.